We spend so much of our time looking for external threats. We look for those sudden, massive shocks that bring complex systems down. But the reality is actually far more disturbing. Catastrophic failures almost always emerge entirely from within.
The most common assumption we all hold is that systems fail simply because a component breaks. A gear snaps, right? A line of code corrupts, or human error is made. We really want to believe that collapse is just a malfunction, a deviation from the rules.
But what if that core belief is entirely backward? Systems don't actually fail because they break. They fail because they work exactly as designed. The absolute greatest threat to a complex system isn't a failure to function. It's the flawless execution of its own fundamental programming, even when faced with escalating constraints. Just think about the contradiction here. Internal sensors are reporting absolute perfect health. All the dials are in the green, the metrics are absolutely flawless. And yet, simultaneously, the entire global structure is actively collapsing. How in the world does a system fracture precisely while it's perfectly optimizing itself? Well, to understand this hidden force, we need to observe a very tangible physical mechanism.
Section 1. The Engine of Stability.
Let's look at the sheer logic of the James Watt centrifugal governor. This was designed for steam engines way back in 1788, and it's elegantly simple. As the engine speed increases, centrifugal force physically pushes two heavy weights outward, and as they spin outward, they pull a linkage that closes the steam valve. Less steam enters, so the speed drops. If the speed drops too low, the weights fall inward, the valve opens back up, and the speed increases.
And the result? The external output remains completely stable. Regardless of minor fluctuations in the fire or the steam pressure, the governor flawlessly preserves a constant speed. It is a closed loop of negative feedback, and honestly, it works perfectly.
Section 2. The Hidden Cost of Balance.
Now, let's escalate things. Imagine we start placing an increasing external load onto this stable engine. We're asking it to pull more weight, to drive more machinery. This mechanical reality actually mirrors a biological one. Think about 37.5. That's 37.5 degrees Celsius, our body's core temperature. Just like that steam engine, our biological systems tightly regulate this metric. If you walk into a freezing room, your core temperature doesn't just drop. Your body restricts blood flow to your skin, it triggers shivering, all to perfectly maintain that 37.5.
But here is where we see the hidden cost. Equilibrium actually masks internal escalation. To maintain an external output perfectly against resistance, something internal has to radically change. You burn more energy, your muscles spasm. And returning to our physical steam engine, as we add a heavier and heavier external load, that governor continues to force the engine to maintain its perfect, constant speed.
But to maintain that perfect speed against massive resistance, the fire has to burn hotter. More coal is consumed. The internal boiler pressure dangerously rises. So the external output looks beautifully stable, right? But internally, the system is being pushed to extreme structural limits just to hold the line. This deeply ingrained resistance to change is known as homeostasis. It is the central motivation for any organic action. But here's the thing, homeostasis is not a state of peace. It's an active, escalating war against the environment. And the more the environment pushes, the more violently the system must internally react just to preserve its stability.
Section 3. The narrowing of alternatives.
Let's introduce another constraint, 143.5. That's 143.5 centimeters, or roughly 4 feet, 8.5 inches. This is the standard railway gauge used by more than half the world's train tracks, and our steam engine is physically locked onto a track of exactly this width.
Now, why that exact width? Well, it was locked in by George Stephenson all the way back in the 1820s. While building the Liverpool and Manchester Railway, he literally just copied the width of the primitive coal tramways he'd worked on previously. There was no grand, optimized design. It was simply a localized decision based on prior limited experience.
The irony is that modern engineering consensus proves wider tracks would dramatically increase performance, speed, and safety by offering a lower center of gravity. But the global infrastructure is already set. We can't widen the tracks now without tearing up the entire world.
We call this path dependence. Actions in the present are permanently constrained by the path traced out in the past. It's an irreversible lock-in. So now, our perfectly functioning engine, desperately trying to maintain its stability, is forced to conform to a historic accident from the 1820s.
Section 4. Irreversible lock-in.
So the tracks cannot widen. Path dependence guarantees this. Therefore, because outward expansion is structurally impossible, the only way to carry that escalating load we talked about earlier is to build a heavier, denser engine. The physical system is becoming massively, irreversibly constrained. You can see a striking biological parallel here when climbers go to extreme altitudes. As the oxygen drops, their kidneys detect the shift and secrete EPO to produce more red blood cells. The goal is to perfectly maintain oxygen delivery, and the system is doing its job. But the unavoidable consequence is that the blood becomes incredibly thick and viscous, severely straining the heart. This chronic compensation masks the underlying failure right up until the moment of decompensation, the exact moment the balancing mechanisms wear out and can no longer absorb the escalating stress. The heart fails not because it broke, but because the blood became too thick in a perfect rational attempt to maintain oxygen. Returning to our mechanical engine, those external demands continue to rise unabated. The load demands maximum power, but the engine is too heavy for those narrow tracks. The boiler pressure is at the absolute limit of the metal, and the friction is just immense. And yet, the governor perfectly maintains the speed. Right up until the very moment the metal fractures, the internal mechanism flawlessly executes its function. It is making entirely rational, optimal adjustments based strictly on its local parameters. We are left with this terrifying contrast. The local mechanism is optimizing perfectly. The governor holds the speed, the kidneys produce the cells. But the global structure is fracturing. The engine derails. The heart stops. When the collapse finally happens, we always look for what broke. But nothing broke. The failure was structurally determined by the perfect pursuit of stability against irreversible constraints. So the next time you see a complex system collapse, don't ask what malfunctioned. Ask what it was optimizing for. The system was never failing. It was following its structure.